Are we looking in the right places for life on Mars? Most of the survey work that has been done so far on the surface of Mars has been done in the southern portion, which are the highlands on Mars. If you study the topological anomalies on Mars, you realize that the highlands may have been created by a large impact that created the Hellas Basin. If that's the case, then we should be looking in the lowlands, which is the northern reaches, for life, because the impact that created the highlands would have destroyed whatever life there might have been on the planet prior to the impact. As a young man, nearly 5 decades ago, I watched with great interest and enthusiasm the landing of Viking 1 and Viking 2 onto the surface of Mars. And of course, one of the key experiments, in fact there are several, related to the simple question, is there life on Mars? That question actually comes in 2 parts. One part, of course, is the question, is there presently life on Mars? And the second part of the question is there indications that there had been life on Mars sometime in the distant past? The first question is a great deal easier to answer than the second. Why? Because if there was life in the distant past on Mars, it probably would have been bacterial. And bacteria do not leave fossil records.
If there is life on Mars, then there will be a simply fabulous expansion of the perspective of the biologist. Because all the organisms on the Earth, even though they seem to be different, are fundamentally the same. Their chemistry is all identical. And they're just wrapped in different kinds of wrappings. Us bacteria, and us people, and us plants, us protozoa, we're all the same on the inside. Now the question is, are Martian organisms the same on the inside as us? Is life everywhere, does it have to be the same as us? Or are we just one example of a vast array of possible kinds of biochemistries? Well, there's no way for us ever to answer that question, no way for us to determine the generality of life on Earth, except by looking for life elsewhere. And the nearest candidate planet is surely Mars.
There appear to be subtle clues that there might be life on Mars. One of the most direct is, of course, the methane plumes that seem to arise in the spring and summer, mostly in the Northern Hemisphere and in the vicinity of Hellas Basin. This is, of course, pointing to the possibility that that life is on the lowlands part of Mars, and not on the part that is the highlands, which may be the remnants of the impact. There are also other clues that go back to 1976. There are some scientists who participated in Viking who felt that there was enough definitive evidence, but the ambiguity still remains. It would be, I think, a wise thing to do to chase the plumes, to try to find the sources of the methane. Perhaps it means going and looking at the interface between the northern lower regions and the highlands. And I think that's something that could be done both using orbital spacecraft as well as landers. I think this should be the next step in the search for life on Mars, to try to sort out what is the cause of the methane plumes that arrive in the spring and summer on Mars. A detailed survey of the surface of Mars delineates a clear distinction between the lower elevation and smoother northern hemisphere compared to the rockier highlands found in the southern hemisphere. At an average height of 2,000 meters above that of the lower northern hemisphere, the volume of materials making up the southern highlands is estimated to be on the order of 1.44 times 10 to the 17 cubic meters. This could be represented by a sphere or bolide of approximately 650 kilometers in diameter. Imagine such a bolide impacting the surface of Mars, melting and flowing with a Reynolds number of perhaps 3,500 radially outwards from the point of impact. This pyroclastic material would flow out radially as a laminar sheet until such a distance that turbulence sets in. Is it possible to estimate the distance of turbulence onset given the size of the impacting bolide? Let us assume a 90-degree change from impact direction to flow direction. When most fluids take a 90-degree turn in a constrained volume, there's a rule of thumb that turbulence will set in at least 3 to 4 times the characteristic distance set by the flow. Here is a picture of water flowing onto the back of a china plate. The water is impacting the surface at a 90-degree angle. The change in flow directions, therefore, is 90 degrees. And you can see a laminar region near the spigot and a turbulent circular region some distance from where the flow impacts the surface. The ratio of the outer diameter, which is the turbulent edge, compared to the inner diameter to the flow, is between 3 to 4 in this example. In the case of the impacting bolide on Mars, this characteristic distance is perhaps the diameter of the bolide. Is there an impact structure that is perhaps 3 to 4 times such a bolide diameter of 650 kilometers on the surface of Mars? Of course there is. It's Hellas Basin. The Hellas Basin has a diameter of about 2,240 kilometers and is a prominent feature on the Mars highlands. The impact that created the Hellas Basin was at a slight angle, but nonetheless you can look at the central feature of the basin and compare it to the ultimate diameter of the basin, and you indeed see by inspection a ratio of between 3 and 4. In this picture you can see an overlay of 2 circles. These 2 regions correlate well with the hypothesis that the Mars highlands are the remnants of a 650 kilometer diameter bolide that created Hellas Basin. The smoother Northern Hemisphere begs the question, was Mars before such an impact in fact a water world, or planet whose surface was entirely covered in water? There are planetary scientists who wonder the same thing about the Earth, that the Earth may have been a water world prior to the bolide that impacted the Earth and created the Moon. It appears that impact on the Earth might have pushed the bottom of the ocean up to above sea level, which, because of the size of the Earth and the presence of a magnetosphere, has provided a dynamic geological history. In contrast, Mars has not been marsologically active over hundreds of millions of years. There is an open question as to whether Mars once had a magnetosphere as well as a thicker atmosphere. Without a magnetosphere, a planet cannot protect its atmosphere from erosion due to solar wind. We hypothesize that future assays made in the lowlands of Mars may show the Northern Hemisphere features to be older than those of the Southern Hemisphere. We hypothesize that if Mars in the distant past had a magnetosphere, such indications might be found frozen within some of the rock features of the Northern Hemisphere. There may also be embedded in these rocks indications of the past atmosphere on Mars. If Mars did indeed have a magnetosphere in the distant past, the impact of a giant bolide may have sent a shockwave through the planet that might have disrupted the spin of the core of Mars. Perhaps this can be seen in seismic studies on Mars. This might also be the cause of the Tharsis bulge. In the case of the inside of the Earth, it has only been recently discovered by geophysicists that there are remnants of such a shockwave that dates back to when the bolide that created the moon impacted the Earth. This shockwave may be the cause of the physical and magnetic asymmetries in the Earth's core. This asymmetry in the Earth's core may be the cause of the dynamic and random periodic flipping of the Earth's magnetic poles. It is possible that cracks or rifts made to the surface of Mars by the bolide's impact may have allowed surface water to flow deep enough into the planet so that we could actually find aquifers. Recently, just a few weeks ago, there was a paper at the proceeding of the National Academy of Sciences in the United States, published on August the 12th, indicating that they have found evidence of underground aquifers on Mars between 11 to 20 kilometers beneath the surface. If the cracks or rifts allowed the water to go deep enough into the planet, this could have been enough to quench the internal heat of Mars. And of course, the now superheated steam might have also vented to the surface via the prominent volcanoes that are found nearly opposite Hellas Basin on the surface of Mars. The venting of large quantities of steam and hot gases would have greatly disrupted the atmosphere of Mars. It probably also would have precipitated the oxidization of the iron on the surface that gives Mars its orange and red color. There may be subsurface cracks now covered over by dust and debris, perhaps somewhere between Hellas Basin and the prominent volcanoes on Mars. Why three volcanoes are in a straight line may relate back to the cracking on the subsurface of Mars by the impact of the 650-kilometer wide bolide. You can see how close the volcanoes in the Tharsis bulge are, and they are almost opposite the Hellas Basin on Mars. Why the three volcanoes are in a line on Mars have never been adequately explained. It is worth noting the distance between the two outer volcanoes in this line is comparable to the diameter of the core of Mars. It is also worth noting that the distance of the line is comparable to the perpendicular distance to Mars Mons Olympus, the tallest mountain on Mars. This may mean that all four features are to a common phenomenon. And again, you may note that the volcanoes are 180 degrees opposite the Hellas bulge on Mars. Perhaps the common phenomenon that made these volcanoes is a shock wave from the impact of a 650-kilometer bolide and how it interacted with the core of Mars. The volcanoes may come from the shock wave diffracting around the posterior side of the core, while the Tharsis bulge may have come from the shock wave interacting with the surface and the anterior side of the core. This is very intriguing. It should be possible to undertake isotopic analysis of signature elements of samples from the northern lowlands and the southern highlands to determine whether they are of a common origin. Such assay isotopes might include zinc, nickel, magnesium, manganese, titanium, and iron. If the highlands are indeed the result of the impact of a 650-kilometer diameter bolide, then there may perhaps be isotopic indicators to this possibility. An assay should also be done on the materials at the volcanoes and the Tharsis bulge. I suspect that sometime in the next 5 to 10 years, if we look in the right places on Mars, we will find definitive proof that life presently exists on Mars. I think we need to stop looking at the highlands and we need to look at the lowlands, or at least in the interface between the lowland and the highlands.
If there is life on Mars, then there will be a simply fabulous expansion of the perspective of the biologist. Because all the organisms on the Earth, even though they seem to be different, are fundamentally the same. Their chemistry is all identical. And they're just wrapped in different kinds of wrappings. Us bacteria and us people and us plants, us protozoa, we're all the same on the inside. Now the question is, are Martian organisms the same on the inside as us? Is life everywhere, does it have to be the same as us? Or are we just one example of a vast array of possible kinds of biochemistries? Well, there's no way for us ever to answer that question, no way for us to determine the generality of life on Earth, except by looking for life elsewhere. And the nearest candidate planet is surely Mars.